Hello everyone, my name is Jorge Isaac and my teammates are Daniela Lucero and José de Jesús. In this project, we designed and implemented a finite state machine traffic light controller using VHDL in quarter span light and the D810 light FPGA board. I hope you enjoy this amazing practice.
Okay, so in order to continue with this, I'm gonna be showing about this finite machine for a traffic light control. As usual, we're declaring the input and output. We're gonna be making an input to of this variable called clock 50 megahertz standby test, and as output it's gonna be clock red 1, yellow 1, green 1, red 2, yellow 2, green 2. Okay, so for the architecture, it is quite easy. We're just declaring it here. The time is gonna be for example, to green, red to yellow, green to red, and yellow to red, and the time test, which is gonna be 1. Also for testing, we're using this max count of number 2, but in order to use it for a real kind of project to be on real life, we shall be using this time, this max count, and due to the fact that we have a 50 megahertz clock and we need to make at least two this number of counts to achieve 1 second in order to divide the clock to get 1 hertz. Okay, so for that part, that's it. Now we have the clock generator. As you can see, it's quite easy. We're just making a counter for this clock 50 megahertz. Um, if as you can see, it's here. We're checking if the counter is it's less than the max count. If that is not the case, we're gonna be making this +1. If that's not the case, we're just gonna make it 0. Okay, so for this second process, which is second out, as you can see, it is quite easy. It has just this clock to be clock state, and that's it of the process. For this another process which has no name, we're gonna be using clock state and standby, and we shall be checking if we have a standby. If that's true, then we're gonna be making the pre-state is gonna be yellow yellow, and if not, we're gonna be checking for every single resting edge of this clock state. For every clock state, we're gonna be making count +1. If count equals to time, then we're gonna be making per state equals to next state. For this another process, we're just gonna be changing the values of the traffic lights. So it's quite easy, as you can see. Okay, so for the VHT, as you can see, we are gonna be using this. I'm so sorry. We're gonna be using these variables for these values to test to be 1 and to standby to be 0. This allows us to use the minimum time just to see it on the simulation. And we're gonna be making this 50 megahertz clock to be changing. And so now let's go to the simulation. Just a second. Okay, so now I have it open. As you can see, it is asking us to have a valid um, license, so we're gonna request it. It shall be quick. Okay, just a second. Okay, now we have it active. Let's go back to this RTL simulation. Okay, so this is now opening. Okay, so this. So let's recompile to check no warnings. So then let's go to simulate, start simulation. This, and this. So that's it. Let's just see this whole signal. Okay, let's just change quickly the names. COK, COK 50 MHS, MH3, green 1, green 2, red 1, red 2. This is the standby. This is the test signal. This is the yellow one. And this is the yellow number 2. So, okay, we are gonna make this in here, this in here, this in here. And that's it. Let's just make this to run. And that's it. As you can see, now we're able to check the values. Okay, so for example, we have first, we have green 2 and red 1 active, as you can see in here. I'm gonna move this here. Yes, so we have red 1 and red 1 it's gonna turn on, and green 2 is gonna turn on. Then we have red 1 and yellow 2, then it's going to change to green 1 and red 2. So that's how this works, and that's it.
And this is a question simulation in which we are going to see the theoretical functionality of this practice. This is basically the traffic lights that we are using. That is as if it was like two street crossing each other. So right now, as we can see, we have red in the first traffic light, and then we have green in the second one. And then we're going to be taking this, and then we have green in the first one and red in the second one. And then we have yellow in the first one and red in the second one. And then we have red in the first one and green in the second one. And this continue to happen as that. We cannot have green in both at the same time, and we cannot have as well red in both at the same time. Um, we also have one configuration that is for a standby. What it basically does is that put both traffic lights in yellow in one. But as we can see right here for this simulation, the standby is 0. And we have active the test so we can check if it's working the traffic light as quickly as we can. And that's it for this simulation. Thank you.
This is the RTL viewer diagram generated by Quartus Prime Light for our traffic light controller. So the RTL view shows how the PHDL code is synthesized into a hardware logic components inside the FPGA. Starting from the left, we can see the 15 MHz input clock coming from the TA10 light board. The signal goes into a counter block, which acts as a clock divider. It divides the original 15 MHz frequency down to a much lower signal, close to 1 Hz, so the traffic light transitions can be visible to the human eye. Then the divided clock output, shown as clock state, controls the timing of the state machine in the yellow block, located in the middle label pre-state. This block represents the finite state machine, which contains all the program traffic light states: red green, red yellow, green red, and yellow red, and yellow yellow. Each of these states defines the color combination for two traffic lights. The test and stable inputs, shown as at the top left, interact with multiplexers and comparators to modify timing and state transitions. The test input allows the system to run faster by changing the time constants to 1 second, while the standby signal forces the FCM into yellow yellow state as safety mode. You can also see several address counters and comparators used to generate timing logic. These components work together to count how long each light should stay on before next state begins. At the right side of the diagram, we can see the output signals R1, Y1, G1, R2, Y2, and G2. These outputs correspond to the red, yellow, and green LEDs, both traffic lights. The logic gates connecting to them ensures that only green and only red are active at the same time, preventing both directions from having a green light simultaneously. So this RTL diagram confirms that our FCM design was correctly synthesized into hardware, showing the connection between the clock divider, the state machine, and the output logic. It demonstrates how our VHDL code translates into an actual hardware implementation on the FPGA. So let's see and go to the pin planner to program the FPGA physically. So here you can see how we can implement the different outputs and inputs into the FPGA. So clock 15 MHz is set as P11, which is the native clock of the FPGA. Clock 2A8, that is an LED output to see the clock working. And these are our outputs, pin as W10, B10, W8, B8, and for yellows we have W9 and B9. For standby, that is an input, that is a switch, we use C10, and test that. So it's an input too, we use C11. So let's see how it works in real life. Enjoy. I hope you will enjoy it.
And this is our project. As we can see right now, is working as the regular way of work. That means it will take like 5 seconds or approximately to change between lights. But if we change this to the test option or the test mode, we can see that it's quicker. We can see that those are changing in a matter of seconds actually. And we also have the other mode, that is the standby. Let me activate it. We deactivate the other one and we activate the standby. And there we have it. And that's it.